boys and girls. Notice that we're now going to start out in a new chapter. And remember what I said at the end of the previous chapter, and that is that we're going to start out with some basic ideas and start building up from there as we progress through this material. And notice that the name of today's lesson has to do with power functions and variation. So let's say a few words about some of these power functions. Well, suppose we were to look at f of x is equal to x, for example. And this is certainly a linear function, one that we have seen before and are familiar with. What we're going to start to concentrate on a little bit in today's lesson, in fact, will be f of x is equal to x squared. Suppose we were to look at, say, f of x is equal to x cubed, and so on. And let's look at going on down here to f of x is equal to x to the nth power, where n, say, is over the set of natural numbers. All right? And these are examples of what we call power functions. So let's give this a heading in which we will call them power functions. And we'll look at one or two cases as we progress through this lesson. In fact, let's look at f of x is equal to x squared and see what the graph of that might look like, okay? And on our coordinate system, we have f of x is equal to x squared. Now, let's take a few points and see if we can't plot those points and see what the graph is going to look like. Actually, I think most of this is quite familiar to you from your work in Algebra 1, but let's make sure. For example, if x is 0, 0 squared is 0, and certainly this point is on the graph, which is right at the origin. If x is 1, 1 squared is 1, so 1 comma 1 is going to be on our graph. If x is negative 1 squared is 1. This point must be on the graph. If x is 2, 2 squared is 4, 1, 2, 3, 4. And also if x is negative 2 squared is 4. This point must be on the graph. Well, let's take one more case. For example, if x is 3, 1, 2, 3 squared is 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. This point must be on the graph, and I think from what you have seen thus far, you suspect that the point on the other side of the y-axis at negative 3, 1, 2, 3 for a value of x, is also on the graph. Would you agree with that? Yeah. And in fact, if x is 4, you get a point way up there, and so on. Now, looking at this graph, as soon as we take as our domain the set of all real numbers, all right, that then will enable us to fill in a nice solid line, continuous line. It is unbroken, coming down on through these points, and then it's going to pass through the origin, and I can't make the graph in that position, so let me then continue on down in this fashion, and our graph is going to look something like this. And the arrowheads indicate that it goes on forever. And we have given this graph a special name from some of your previous work. And does anybody happen to remember what the name of that graph is? And Tim?
Parabola.
A parabola. A parabola. P-A-R-A-B-O-L-A. This graph is a picture of what we call a parabola. Now, there are a number of characteristics that we may look at just as we are looking at this picture. For example, suppose I took any point, let's say that the coordinates of this point are r comma t. All right, I come out here some number r, and I come up some number t. And associated with a point, there is a corresponding point right over here, which is going to have what coordinates? If I come out here r, the same distance on the left side of 0 is going to be equal to, Bill?
The opposite of r, comma
It's then
t.
the opposite of r, comma t. Is that right? And when we have these 2 points on the graph, all right, then in fact we're going to have an axis of symmetry somewhere. And where is this axis of symmetry in the case that we have right here, Doug?
The y-axis.
It's going to be the y-axis. Does everyone agree with that? In that the y-axis is what we will call an axis of symmetry, as we have on this picture right here, all right? An axis of symmetry. Now notice that because we have here x squared, that is 1 times x squared, all right? We know that any number when squared is always going to be what kind of a number? It's always what? A positive, or in fact it can also be 0, so we say that it is what? Non-negative. Our graph is going to open upward, so to speak. Is that right? It's going to be in this position. And if it's going to open upward, therefore this point right here is going to be called what? It certainly is going to give us the smallest value on our graph that we can have, and we give that a special name, and it is called the what? Well, the minimum value. The minimum value, okay? Now, notice that we're dealing here with x squared. And what I'd like to do is to put on the same coordinate system, if I can squeeze it in here, the graph of f of x is equal to x to the fourth power. And let's see what it looks like. For example, if x is 0, 0 to the fourth power is still 0. X is 1 to the fourth power is 1. Negative 1 to the fourth power is 1. Those 3 points are still on the graph. Now, I know that we can't squeeze it in, but looking at x squared again, for example, if x is a half squared is a fourth, but a half to the fourth power is what? Is a 16th. So certainly between 0 and 1, the graph of x to the fourth power is going to be below that of x squared. Is that right? Now, when x is, say, 2, we know that 2 squared is 4, but then 2 to the fourth power is what number? Is way up at 16. So now when x is 2, we here is 4, 5, 6, 7, 8, and way up here somewhere off of our graph almost. Is that right? And similarly, when x is negative 2, we have a point which is way up here. Now, if I then were to come in with a dotted line, you can see that this dotted line is going to be inside the graph of x squared. It's then going to pass through this point of negative 1 comma 1. It's then going to be outside the graph. It's then going to be quite flat, passing through the origin, outside the graph, passing through 1 comma 1, and then it's going to be inside the graph. Does everyone agree with that? Okay? And that then is the graph of what? X to the fourth power. But notice it is still a shape which opens upward. Is there still an axis of symmetry? Yes. Suppose we were to look at x to the sixth power. Do you think that would be even inside of this one? And so on. So in fact, any even power, x squared, x to the fourth, x to the sixth power, is always going to be symmetric with respect to what? The y-axis as we see it in this picture. Now notice too that the coefficient of x squared here is 1, the coefficient of x to the fourth power is 1, and so therefore the curve is going to open upward as we have it in this picture. Well, let's look at a second example, and what I have here is a curve which is a parabola, certainly. Let's look at the solid line first, but it happens to open downward. Now the axis of symmetry is still the y-axis, but can anybody give me the equation, the formula for which we have here this solid line? Steve?
Function of x is equal to negative x squared.
F of x is equal to the opposite of x squared. Is that right? And this opposite symbol has the effect of taking our first graph, looking here again at example 1, of x squared, and flipping it, so to speak, across the what? Across the x-axis, and we see then that we have our curve which is going to open downward. Now we still have our axis of symmetry here, which is the y-axis, but the fact that we have this curve opening downward, right here at the origin, we are going to have what? In this case, it's going to be a maximum. Okay, here we have a maximum point. That word there says maximum. Everybody can see that. Now, looking at the solid line, from what we have said in example 1, it looks like the function, the equation for the solid line is going to be what formula? And, well, again, from the symmetry and everything else that we have here, Tom?
F of x equals the negative of x to the fourth.
F of x is equal to, let's use the word the opposite of x to the fourth power. Okay? Well, what I'd like to do now is to turn to a third graph in which I would now like to look at, let's say f of x is equal to x cubed, and see if we can't make its graph, in which we now want to deal with an odd degree polynomial function here, okay? Now, again, if x is 0, 0 cubed is 0. If x is 1, 1 cubed is 1. If x is 2, 2 cubed is 8. 1, 2, 3, 4, 5, 6, 7, 8, and we're almost off our graph. And if x is 3, we're way up there. Now, if x is negative 1 cubed is what number? Negative 1. And now notice our graph is then going to have to come down in this direction. Perhaps we should take a point, say x is a half. And if x is a half cubed is an 8. Is that right? And I'm just a bit up here. Now, if x is negative a half cubed is negative an 8, and I see now, I think you'll see what's going on. If x is negative 2 cubed is negative 8. 1, 2, 3, 4, 5, 6, 7, 8, and this point must be on the graph. Now let me see if I can make a rather accurate sketch. Again, as soon as we take for our domain a set of real numbers, That then enables us to fill in with a nice solid line our graph. It's going to pass through these points. It's going to curve here. It's going to have to go through the origin. It's going to have to curve on down, and so on down through these points as we have in this picture right here. And this is the graph of a cubic, x cubed. Now, notice that if we take some point, or any point, let's take this point right here, of r comma t, all right, now associated with a point, and if I were to use this straight edge, a point through the origin, all right, on the same side, or on the opposite side of the origin, as the given point with r comma t, I have a point over here which has what coordinates? This is the opposite of r, comma, the opposite of t. And when we have these 2 points, r comma t, and the opposite of r, comma, the opposite of t, on a given graph, then in fact we have this origin, all right? It's the origin which is a point of symmetry. We speak of a point of symmetry here. And I think that you can see that this will be the case as we have in this picture. If the point were up here, and the corresponding point of symmetry is then going to be one on this side, is that right? And this is a characteristic of a graph which is of a pattern x cubed, x to the 5th power, and in fact it's going to be any odd-numbered power function which is going to have that characteristic, okay? So the origin here is going to be its point of symmetry. Well, let's then look at, say, f of x is equal to x to the 5th power and see if I can't squeeze it on this graph. Again, if x is 0, 0 to the 5th is 0. If x is 1, 1 to the 5th power is 1. If x is negative 1, negative 1 to the 5th power is negative 1, so certainly those points are still on the graph. Now, let's come back to x cubed. If x is a half cubed is an 1/8. But if x is a half, 1/2 to the 5th power is a 32nd. So it's going to be below that graph, is that right? And below this, and you can see I'm having difficulty trying to squeeze it in. If x is, say, 2, 2 cubed was 8, but 2 to the 5th power is way up at 32. So without too much ado, let me now put in a dotted line here to distinguish this from the first one. Now notice I'm putting in a dotted line simply to make the graph. But indeed, we had over the set of all real numbers as our domain, and our graph is then going to have to be below this one, through that point, below this curve, through the origin, above that one, so to speak, and continuing on through this point, and it's then going to be inside this graph on forever. Is that right? And that then would be the graph of f of x equals x to the 5th power. Well, let's look then at a fourth picture, and in this case we have a solid line first, in which our graph is going to have what formula? Can anybody just look at that, and from what we've just said, Bill?
F of x equals the opposite of x cubed.
F of x is equal to the opposite of x cubed, and now the graph of the dotted line is going to be, anyone? Steve?
F of x equals the opposite of x to the 5th.
The opposite of x to the 5th power. Now notice, let's come back here to graph number 3. Now notice that as x moves from left to right, as the value of x increases, all right, the value of the function is increasing from left to right. Is that right? Whereas, now as soon as we take the opposite of that, that has a tendency to flip the entire graph around the x-axis. Is that right? The graph is going to flip around the x-axis, and when it does so, you see the opposite of x cubed, which is then going to be the solid line, which as x increases from left to right, the graph is going to decrease. Okay? Well, so much for this. What I'd like to do is to turn a little bit to another topic in which we may think in terms of what we will call direct variation. And this is really just an application of what we have been doing thus far. For example, if we say y varies directly as as x squared, what then is a formula that we may write for this description as we have here? Y varies directly as x squared. See, we're bringing in a power function, and who can give me a formula which we may write here? What do you think about that, Peter?
Y equals mx squared.
Y is equal to m times x squared. Good, where m happens to be some constant of variation. Is that right? And if we were to say y varies, or is directly, let's use that phrase, is directly, D-I-R-E-C-T-O-A, directly proportional, all right? Directly proportional to, let's say x cubed. what then is a phrase? Give us a formula which we may use in order to interpret this phrase and this sentence as we have here. And can anyone think of any, how about y is equal to, what can we say there? Kirby?
mx cubed.
M times x cubed. And we may also think in terms of direct variation in terms of these power functions as we've been dealing with right now. Okay? Let's look at an example of this. And here we have the distance a body falls from a position of rest varies directly as a square of the number of seconds it falls. Now, if a body falls 64 feet in 2 seconds, how far will it fall in 5 seconds? So let's then take the first sentence. This is really quite straightforward. The distance a body falls from a position of rest varies directly as the square of the number of seconds it falls. And give me a formula then which will interpret that. In terms of, let's say, d would be the distance, and t, say, would be the number of seconds. And what can we say about that, Doug?
D equals mt squared.
D then is equal to mt squared. Is that right? Now, for a particular value of t, that will give us a particular value of d, which I'll call d sub 1, okay? It's m times t sub 1 squared. Does everybody see this notation? Now, for another value of t, we're going to get some other value of d. Let's call it d sub 2, which is then mt sub 2 squared. Now, please, this little subscript notation is a sub 2, and this number 2 is squared, okay? Now, looking at this, you say, well, if I were to divide through by t sub 1 squared, I have m. And if we were to divide this one through by t sub 2 squared, we'll also have what? M. Therefore, what is our conclusion about these two statements? What can we say but that they are equal? Therefore, d sub 1 is to t sub 1 squared, as d sub 2 is to t sub 2 squared. Now, again, we're right back to a case as we have done before. We have 4 numbers here, of which we should know 3 of them, and we can easily solve for the 4th. Let's now come back to our data. If a body falls 64 feet in 2 seconds, so we have 64 is to 2 squared, which is 4, as how far will it fall in 5 seconds, as d sub 2, which we do not know, is to 5 squared, which is 25. Okay? Now let's just solve this little equation for d sub 2. We have what? 4d sub 2 is equal to, what do we have? 64 times 25. D sub 2 then is, let's see, 4 divided 64, what, 16 times 25, and let's see now, 25 is 1/4 of 100, and 1600 divided by 4 is, what, 400. So, therefore, what, the distance it falls, the object falls in, what, in 5 seconds is, what, 400 feet. And that then would be the conclusion to the original question. Let me give you your homework assignment. I think that's all that we need to do for today.